Hello and welcome to lesson 11-4, which is all about normal distributions, really important topic in Algebra 2. By the time we're done, we want to be able to understand where a data value falls in relation to other values in a normal distribution. Okay. So the first little bit that we're going to do is to look at the Explore and Reason.
Caution, there's a slight error in your student companion. They switched the placement of the two graphs.
But they left the mean and standard deviations in the right places. So you just need to put an arrow. So this mean and standard deviation go with the apples, and this mean and standard deviation go with the oranges.
That's in your student companion. Here we have it correct. So we are going to just leave it because they do match here.
Okay. So the first thing we're going to think about is describing the shape of each distribution, how they're alike, how they're different. So the shapes of these, I kind of like how the fruit is showing behind these. It's kind of fun. But easiest way for us to think about this shape is to kind of trace the outer edge of our data. So both of these, what would you call these, mostly normal?
I would. Okay. I do think so. Even though this one doesn't, it's more of a mountain, it doesn't kind of have that change from concave to convex. I still would think they're both fairly normal.
Yeah, and I might even say, yeah, this one almost looks like the highest points are a little to the left. So I'm a little tempted to say right skewed, but I think.
Well, and what we really want to think about, and one of the things that we're going to talk about in this lesson is where's the majority of the data. Like when I think of the majority, I'm thinking, 2/3, about, most of the data. And it's going to fall in the center on both graphs. And so I'm thinking about that. I'm also thinking about where the mean is and where the median is and where the mode would be. Because in our last lesson, we did talk about how those fall in the same spot on a normal distribution.
True. Is this one a smooth mixed page?
All right. Part B says use structure. Explain how you could estimate the mean from the graphs. A standard deviation measures spread from the mean. Which data values are within a standard deviation of the mean? So we're just eyeballing this idea.
And they've given you, can I see the pen? They've given you what the mean actually is. So 1750, okay, that'd be in here. I don't know if you guys talked about it kind of being a fulcrum or a tipping point, or you could balance point. So 1750, if they hadn't provided that, you might have thought it was going to be around there because that would be your balance point. And then same with 210 over here.
I might have put it slightly to the left, but I would be pretty darn close to that. Then I'm thinking, okay, well, that same idea, I'm thinking like out to here would be about 1 standard deviation based on my kind of rudimentary knowledge going into this lesson and about here. So having it be 47 kind of really jives with what I would think it would be over here, about 300. So again, we're kind of like, oh, that middle, like we're kind of just tapping into the middle portion of that data where the majority come. We always get a habit of mind. How could you calculate an exact value for the mean and standard deviation for either of these distributions?
So,
or could you is the actual question.
I was just going to say, so could you, if this was all the information you were given, I don't think you could calculate it exactly. You could estimate, but not calculate exactly. Whereas if you had the data set, a list of data, then there are ways you can do those calculations, right? Because we know, like, for example, mean, we'd add them all up and divide by how many there are. Okay, so this is the empirical rule. This is the big deal, famous one that you'll never forget after this. So the normal distribution has a special property called the empirical rule. The approximate percentages of any data falling in the interval of the range of the data can be determined using just the mean and the standard deviation.
These are two symbols that they don't really introduce you to enough. I suppose they're right here, but from this point forward, you are going to be expected to know them and recognize them. And so,
and up to, we were using X bar for the mean previously. And now we're gonna switch to this, it's called mu, that fancy U shape. So sometimes you'll see it that way. No, don't make it a minus though. Yeah. So standard deviation and X bar are ones that you'll also see, but this textbook is gonna use mu and sigma.
But you kind of got to be familiar with all of them, because when you're working in your calculator, when you're working at decimals, you'll need to be able to say, oh, in my TI 84, that's the mean on top. Later on, they're going to show you the standard deviation that way.
And the big empirical rule, the big huge idea here is that 2/3 of the data is within one standard deviation of the mean. So if here's the mean, that's my balance or my tipping point. And then I always make like kind of almost like parentheses around there, like forward, because I'm adding one standard deviation and subtracting one standard deviation from whatever the mean is. And then that kind of makes like walls, and within the walls here, 68% of our data, roughly, since we're estimating, but it's right around 68% of the data should be in there.
It's relevant to say that this curve is like an area model where we have 100% of our data underneath the curve. And so when we're looking here in this middle part, we're like, okay, so that's either side. Like I'm 5'5", I'm kind of the most normal height, or the most average height for women you can be. And so I would fall right in the middle, but most women are gonna fall within one standard deviation, either shorter or taller than me. And so it kind of helps me understand.
Yeah, so if you were given the standard deviation of 65 and maybe the mean of 65 inches or 5'5", and then you were given the standard deviation is 5 inches, say. So you'd go out to the left and to the right and say, okay, 70 inches and 60 inches. I don't know, depending on your data set, I guess, if that's realistic, but then you kind of draw these walls up and you know that 68% of women are between 60 and 70 inches tall. So just to kind of like, I know this is a little, with all the variables, it's a little abstract, but that's the idea.
Yeah.
So then keep that example going. And if you think about, okay, within 2 standard deviations, so she's gonna go 5 more to the left, 5 more to the right.
And this is actually like spaced out such that this is 5 away, this should be 5 away also. I mean,
just 5 inches.
Yeah. Or 5 units on your graph, whatever. So this would be 55 inches and this would be 75 inches.
Assuming, so maybe I should write that, like if you would assume 65 inches was the mean and 5 inches was the standard deviation of the group that you measured. So what we know is that within 2 standard deviations, so now she's got 2 left and 2 right of that, there's, in this section in between there's 95% of all the data would be in there.
Which is so cool because it's like, okay, so people are, like not that different in this big group. And when we get outside of that with 3 standard deviations, we're going to come out here and now we're going to be from 50 inches all the way to about 80 inches.
And then 99.7% of the data would fall within that. So up here, 99.7. So, and then beyond that, it's a 100% if you're in the four standard deviations away. Notice this rule only applies to normal distributions. That's important. So if you're skewed left or skewed right, all bets are off. You don't use the empirical rule.
Absolutely.
Was that enough? I want you to not be intimidated by this notation. Mu is the mean, mu plus 1, mu plus 2 of those standard deviation balls.
I think we'll get into it a little bit more with our first example, but this is such a huge, cool idea. And so I know that you'll have notes on it. And so we won't go any further there, but so as you look into your online textbook, you can push play here and you can kind of watch. This is a Scottish men's survey. And so we won't play the whole thing here for you, but I would encourage you to watch it and know about how the empirical rule helps you. The empirical rule is also called the 68-95 99.7 rule. So if you go online and you're like, I want more information, you can refer to it as either one of those.
You won't know the upper and lower boundary values for a whole population in the study just by knowing the average and the standard deviation. The empirical rule only covers 99.7 of the values, not the farthest from the mean. So there could be an outlier way out there that is not considered, and that's just part of the error of the rule.
Since we didn't watch the video here on our video, we'll kind of walk through this a little bit more as our example. So the chest circumferences range from 33 to 48 inches with a mean chest height of 40. So as we're building our sketcher, we've got 40 in the middle as that.
Tipping point. Scottish men's chests.
I think so.
What would you expect to be the smallest and largest chest measurements of the middle 95? That light bulbs come off when I see 95% of the mean. So we flip back to the page before and you see that in order to stay with 95% of the data inside, we're going to be 2 standard deviations away, on the left 2 and on the right 2.
And it's kind of nice that they built this graph for us. You should definitely write this down and you should definitely be making the sketch.
Yeah, draw the sketch for every single problem.
And it's okay if your normal curve comes out like a little lopsided on one side. That's okay. You can still use it.
Yeah, then you just label it carefully. So 40 was our mean. And then we did 1 hop of 2 inches, 2 hops of 2 inches. And now we're 2 standard deviations below. 1 hop of 2 inches, 2 hops of 2 inches, and they just happen to have these labeled by 2, so that works.
I kind of like to do that when I build my own graphs, is to label the standard deviations away.
So here we would say the smallest would be 36% and the largest would be 44%. If you put all those people in the room, you've got 95% of the people.
And so that's in between here. So Mrs. Conway, if we've got 95% in between, what's on the corner
Well,
here?
I know 100% is going to be the total. So 100% minus the 95% leaves 5%. And that's divided between the left extreme and the right extreme. So that means 2.5% of the people have chests bigger than 44 inches. And 2.5% of the people have chests smaller than 36.
And I want this arrow to go the other way. Well, and so that's so interesting because so if you had a chest width or chest measurement circumference of 36 inches, you'd be in the 2.5 percentile.
Yes. So like if you ever go to the doctor and you get the printout from Black Hills Peds, they'll say your child's head circumference, when they're babies, they always measure the head circumference, but they'll say your child's head circumference is in the 70th percentile. Then you know that head is bigger than 70% of the other children. So
if it was 40, it would be in the 50th percentile because in a normal distribution, that's our median, that's our mean. And so we would say that that's the 50th percentile. Over here, we probably say 100 minus 2.5, that would be our 97.5. A little extra
preview to other things.
So what would you expect to be the measurement of the 16th percentile of men with the largest chest populations? And again, this goes back to that same idea. 16, I'm like, I've heard that before.
16 is half of 32.
And if I'm in this middle spot, there's 68%. That leaves, again, we'll do that 100% minus 68%. That gives me 32%. Well, you might not have pinged on that, but half of that is 16. And so that would make, if I'm going from left to right to this point of 42, that'd be 68 in the middle, 16 on the left. So this would be the 84th percentile, right? So, and what would you expect to be the measurements of 16% of the men with the largest chests in the population? The largest, so that means we're going to be in this 16% over there. So 42 or greater. Yep. Ooh, that was fun. I like the normal distribution.
Me too. It's so cut and dry. Like, you get the number, you see where it is. Like, you don't have to guess much.
So in this, we're going to use the empirical rule a little more. We probably previewed a little bit on that one.
So recent SAT scores for college-bound seniors
This is
are
very common.
normally distributed with a mean score of 508 and the standard deviation of 121. Like, I can't even read the rest of the question. It said normally, I'll read it in a second, I really will, but it said normal, so I'm doing that. It said the mean is 508. And then I just make my increments on my picture, like on my x-axis, match with, see, here's an example of a not well-drawn one. It'll still work fine.
It will still work.
But then I know my standard deviation is 121. So I'm gonna add 121. So 508 plus 121, whatever that is. And then I might even end up adding another one. So it would be that plus 121 again. And then, so it's like, I kind of just map this out right from the start. This would be 508 minus 121 and so on. And so what proportion of students receive scores between 387 and 629?
Ooh, 387,
I
right
was just
here,
gonna say,
right here.
did you just go to calculate those for me?
I didn't, but I could.
387 and then 629, 5, yep, this is it, 629. So basically, they're just asking between, I did one standard deviation. How do you write it? You write mu plus 1 and then that sigma. And then this is our mu and this is 1 minus, or mu minus 1 standard deviation. And so I think it's kind of helpful to put this notation in the bottom as you go to, just to get yourself used to it. But so 68% is definitely going to be between that. I bet you
I bet they have a beautiful picture.
I bet they do. I bet they draw that for nothing.
I don't know. I think the thought process involved in how to make that curve is super valuable. So,
Oh, look how good it is. I really do like theirs. You can take mine off. Theirs is better.
I don't know. I think that's
I like how they're showing a little jump left, jump right.
right.
Yep. 68% of scores are within one standard deviation of mean. That means 68% of the kids are there. Do you feel like doing the standard,
I think we'll get there. I think we'll get there because where we're going is she took the SAT, I took the ACT. Who did better?
oh, that's not what I was gonna say. But I
Research.
was just gonna say, what was my percentile? So if I
Oh.
got 629, what percentile would I be? Because I know that
So just
if I got the 629 right here, I'm one standard deviation above the mean. So we talked about 68% of the data is in here,
so 68 is between here.
which means 32 is outside of it, which means 16 on the back end and 16 on the front.
Well, and I don't want to say, I don't want to be outside. I want to be, I mean, it is outside, but it's in this space, still under the curve. That's where
That's
that 32% is. And so we've already discussed that this would take us to the 16th percentile. So this would be the 84th percentile.
So if I got a 629 on that thing, I would know I had a better score than 84% of the people.
And if I got a 630, then I must be slightly better than 84%. But I don't know how to do that yet.
Not yet. Oh, but soon. Yeah, what if you got a weird number? Good deleted.
Come on, computer. Okay, so now they're talking about SAT. And again, I still
That
have
was
like,
before.
what's that?
It was SAT before.
Oh, it was? Oops, yep. So I still am drawing my curve. I'll just go ahead and,
Wait, you go back. Oh yeah, go ahead.
what proportion of students?
So this is, we kind of,
Oh, we jumped right
Well,
ahead of this one. We
yeah.
already talked about it.
so 16%, if you had a 387,
This is exactly what we just talked about.
16% scored lower than you. So then you just, I mean, there is an element of you do have to read the question really carefully because they're asking scores greater than 387, whereas I might jump down 387, oh, 16%. But it's like they want greater than. So
Well, and in statistics, then you're gonna be talking about this side of your curve, or are you gonna be talking about this side? And I'm a little sloppy there, but when you look at your table, it'll be either a right tail table or a left tail
Oh, yes.
table. And so when we're thinking this, we need to look on which side we're asking. I think that's a good step. Do we look at that?
consulting an accurate sketch of the distribution under consideration will help determine whether the empirical rule applies. So it applies if it's normal distribution. I always look for the word normal in the direction too.
This is very, very parallel to what we just talked about. So we'll let you try that. And
Now we're
we'll
gonna be 2 standard deviations out. So 2 to the
add
left,
to
2
your
the right.
diagram that you already have.
Okay, here's where you were talking about comparing. Okay. So Ella and Alicia are comparing scores on the college entrance exam, which I think this is very, like, we do this all the time. Ella's SAT score is 1380. Alicia's ACT score is 32. Well, they're not scored the same. So it's not like 1380 is a bigger number, so she did better, because you don't get to 1380 on the ACT. So the mean SAT score is 1,000 with a standard deviation of 200. The mean ACT score is 21 with a standard deviation of 5. So who has the better score? What we're going to want to ask is whose percentile is higher. So here's the SAT, here's the ACT, and here's where these people fall. And it looks to me like they're each 1 standard deviation or 2 standard deviations above.
Slightly. Ella looks like she's slightly under 2, and Alicia looks like she's slightly over.
But what it's kind of making things in the same scale, if you want to think of it that way.
Yeah.
Like 100% is not just 100%. So then this is like comparing apples to apples.
And I think of fractions, like we always turn fractions, part whole fractions into percentages in order to compare them.
Oh, yeah.
It would be similar with finding what we call a z-score. Right?
Most data values are not exact integer numbers of standard deviations away. So we need to find a way to describe a fractional number from the mean. So it looks like, if I had to guess, if I'm saying from here to here is 1 standard deviation, Ella's score might be 1.9 standard deviation.
And I jumped a little ahead saying that was a standard deviation away, and I shouldn't have done that. I'm not so.
Oh, yeah,
it was labeled that though, but
usually we do that. We label those.
But this is a huge idea, this idea of a z-score. So it counts how much, the z-score is a count of how many standard deviations the data value is above or below the mean. And
I just love that, because I always thought z-score is something real abstract, like really like, oh, that must be so hard.
that must be an 8
But it's not,
stats
it's
thing.
just how many jumps of a certain size did it take?
So we're like, okay, we had those real numbers there, and now we're gonna standardize them.
And if we went 1 standard deviation away, like somebody's score was 1 standard deviation above, for example, the z-score is just 1. Like, it's really easy.
Okay, I got my sketch.
So there's a formula and everything, but I don't want you to lose sight of like what it actually is. It's not.
No, it's just how many standard deviations a data value.
So the first thing you do is figure out how far away from the mean your number is. So for example, 1380 minus 1,000, because 1,000 is the mean, it's just seeing how far above, how many points above was it?
She beat the mean by 380 points.
Yes. And then since standard deviation is 200, that was 1.9 standard deviation jumps forward. And then same thing with Alicia, her standard, she was 21 minus 32 minus 21, 11, 21, right? 11 minus, or divided by 5, because we want to know how many groups of 5 is 11.1.
So she did, well, we're thinking that so far. Sometimes you'll see this written as x minus x bar over sigma.
Yes, that's how you'll see it probably all the time now from here on out.
But we put our real data value in, we take away the mean. So we're finding, if you're below the mean, you're gonna be negative. If you're above the mean, you're gonna be positive. And that's something that will be important. Next. So, like we said,
Making sure to answer the question at the end also.
but looking at that and then looking back up at that graph, we can see that she's just a little bit above that second standard deviation. She's just a little bit under. That was 1.9. That was her z-score. And right here, she was 2.2. That was her z-score. Okay. Common error. You may think that a positive z-score is always better than a negative one, but be careful to consider the context, because sometimes that's not true. And do we have a habit of mind? Okay, we did. So this one, you're going to compute the z-score and compare them once again.
How many examples should we do? So this is just exactly like the Ella and other girl, and so that will be doable. That,
Oh,
try
yeah,
it.
you can do that.
Yeah.
Very similar.
okay, the weight of a captive adult female lowland gorilla is normally distributed with a mean of 82.3 and a standard deviation of 15.33. Calculate a Z-score for Sasha. How can you use this score to find the percentage of captive adult female lowland gorillas whose weights are less than or equal to hers? So just exactly like we did before, I just can't help it whenever people say the mean and standard deviation. I mean, you just almost have to write it down. So this is at 82.3 is where we'll find our middle.
But
And
you
then
only trigger into that because it said it was normally
Normal.
distributed.
Right. And then we're thinking about increments. So if that's my mean, then I would make increments that are standard deviation size.
15.33 away.
Yep, so I would take 82.3 plus 15.33, and that's how I label that one. And so, and in fact, I bet you that's what they did. Oh, they didn't show us a picture, but that's okay. What they did is they took her weight, 61.8 from the, just shown in the diagram here is where I got that information. And then minus the average, and so we could calculate how many actual pounds or kilograms lower than the average was she. Divide that by 15.33 to find out how many groups, because that's what division does, how many groups of something. So how many groups of 15.33 was she below the mean?
So how little was she? Should we be worried? That's what I think parents think when they see that.
Mhm.
Oh, there's your diagram.
Thank you. Notice they put 0 in the middle.
So since they put 0 in the middle, this is a standardized curve. So when we make this division and we find that Z-score, our new mean is like 0. And so 1 standard deviation, 2 standard deviations, 3 standard deviations above, same going the other way. And when we locate our Z-score, it's now kind of standardized.
So 0 on this picture still represents that average weight. And 1 still represents 1 plus
15.33 in this case.
added on to the average.
Now we actually talk about percentiles. We've kind of been talking you through them a little bit since the beginning, but the percentage of values less than or equal to a particular data value is equal to the percentage of the total area under the distribution. And this is that idea of that area under the distribution of the curve. And so we went from talking about histograms to talking about area under the curve. And so they kind of divided it up and made this really nice curve. And we're talking about the percentile, like how much of the data is to the left, how much of the data is to the right.
And it's always going to be given as a percentage because you don't always have 100 pieces of data. So if it's 1,000 pieces, you'd still be able to figure out about how many people in your group using the percentage.
If it was 20 people. Now we head to your TI-84 graphing calculators. And, or there's 3 different ways that we want to introduce you to this idea. Because once you compute a Z-score, if you're at your house, you're like, well, I know that it's in between 1 standard deviation and 2 standard deviations below, and you might have marked those percentages in your head or on your normal curve. But what mathematicians have done is they've calculated this using calculus and using a little higher level math than we're in currently, but they've calculated it so that we can refer to it. Normally we have a printed table, but we also have technology that can support us. And so Mrs. Conway, as I was kind of talking there, went to Desmos, and what she types in here is just normal distribution. So normal dist. And so what we're going to look at is the cumulative probability under the curve. And so here's our little curve. It's centered at 0 or on the y-axis because that was what we just did. We just found that z-score and that became our mean. Now she clicked the little button to zoom us right in. So here's the most perfect normal curve that I could never draw. And when we put in our negative 1.34, what we're going to be looking at, I think you need to put it as the max or.
Oh, yeah.
So what we're looking at is all the way from the left, all the way out here, negative infinity. We're looking at this interval all the way up to negative 1.34 because that was our z-score. What our calculator plunks out is this percentage as a decimal. It's a decimal calculation of how much area is in this red space. And so we see that about 9%, that would be the 9th percentile. So that little baby monkey, gorilla, is it a gorilla? Was in the 9th percentile. So Sasha was our star of this problem, and she was in the 9th percentile. What they have here is on your TI-84, what you can do is you can find this button, and I'll just grab one here and kind of show you. You can't see me in my little tiny corner there, but if you go second and hiding behind the bars button is DISTR. That's our distribution, so you're going to get some different functions there, and we're going to go to number 2, normal CDF, and then when you're there, you have to put in that negative infinity, that way left side, and so that's what they're doing here with this number. They're putting in way left, negative, the smallest number they can, all the way up to our z-score, and then they're saying for a normal distribution with a mean of 1 and a standard deviation.
A mean of 0.
Oh, thank you for catching that. A mean of 0 and a standard deviation of 1.
So then I think I could put my gorilla information in there if I wanted it to adjust. So instead of having a mean of 0, I think I could say, but
8 point, or what was our numbers up
Yeah.
higher? We have to make sure that we put them in correctly because we have all the way at the top, we have our
average of 82.3 would go in the place of the 0 on that, and then the 1 in place of that would go to 15.33. And then we should get the same output either way because the percentage won't change. The other thing I would like to look at, and I haven't, I can't show it to you right now, but I think Excel spreadsheets. I think that's what they're showing here on the
definitely.
right. They have commands, and we could just Google it. That's what I'll do later on. Is just Google how to do normal distribution percentiles on Excel.
The other thing that you'll want to know how to do is use a table, and your teacher will probably show that to you in class, but what you do is you look up that z-score and then read the percentage.
Why is the z-score a good measure to use to compare data values from 2 different normally distributed data sets? So thinking about standardizing information, like I think the ACT and SAT, I mean, you have 2 different scoring mechanisms, but you can compare them in a way that makes sense to see whose score is actually higher.
I think last year we had a problem where we compared Harry Styles and Selena Gomez's
height. I'm gonna find that one.
But one is a male, and so the average male height is different than the average female height, and so they were saying who is taller or shorter relatively.
Yeah.
And so we can't compare them to each other because they're not exactly the same. But when we use the z-score, we could say compared to other men, she was in the 50th and he was in the 51st.
And he compared to
Yes.
I like that. We should find that one.
That summarizes this section.
Awesome.
Super job out there. You need a little practice. You have to play around with those curves and playing around with those percentages. So if it's a little scary at first, like Mrs. Conway said, don't let it be. It'll be great.